Lesson 7.3, special exponential functions. So I'm seeing this character e show up as a base. Now, e is approximately 2.71828. I introduced this to you guys back last week. Actually a character on your calculator. So if you hit second and this L and key, it'll bring up e to the x. So e to the something, type in 1. E to the power of 1, of course, is itself, which is e. And there it is, 2.7182. Okay. How you can get this with the limit. Here's a little bit of calculus type notation here is as x approaches infinity, 1 plus 1 over x, all raised to the power of x. Okay. See, like there's this trade-off between x making this fraction small, but making the power big. Right? Like here, if you plug in something small for x, like 1, so we have 1 plus 1, which is 2, 2 to the 1 is 2. Okay. Well, what if x is like 10, right? Or 100 or 1,000? See, this fraction is getting closer, closer, closer to 0. So you're getting 1.1, 1.01, 1.0001, right? And this is a whole bit in parentheses is approaching 1. Right? But this power, by contrast, is exploding bigger, bigger, bigger. It's 10, 100, 1,000. Right? So 1 to the power of anything should just be 1. But anything to larger power should get larger, right? So you have this weird trade-off. And let me show you guys that what if you plug in like 1,000 for x? Watch this. 1 plus 1 over 1,000, okay, which itself is like 1.001, which is very, very, very close to 1. Okay? What if I raise that to the power of 1,000? Do I get something close to this? Let's see if it is. 2.716 something. Yeah, that's almost 2.718. It's very, very, very close. Okay. What if I make this 10,000? Throw an extra zero right here. Okay. 2.718 something something. Yeah, okay. Now it's getting even closer. Okay. Now if you let x go to a million, a billion, a trillion, and approach infinity, which approach it. Okay. So what is this number good for? E equals 2.718. Right? Why is it a number that's stored on your calculator? Okay. Um, well, there's some place where it'll show up. Let me tell you one interesting thing about the graph y equals e to the x. Okay? And they have it right here. F of x equals e to the x. Okay? See, okay, so it's just look at an exponential curve. You guys have seen those for a few days now. Okay? If you hold your ruler flush to this curve, now if you go to the left, the ruler is almost horizontal, right? Almost indistinguishable from horizontal, right? But as you go to the right, see like the slope gets steeper, steeper, steeper. If I just hold my ruler flush to the curve, like right at this point, bam, right here. If I hold my ruler flush to the curve, I see there's a slope. There's a rise over run, rise over run. What is that slope, that rise over run equal to? It turns out that it's exactly equal to the coordinate of this graph. So at the coordinate 1, comma 2.718, if I hold my ruler flush to that curve at that coordinate, the slope is also 2.718 over 1. It's the same, right? This is the only curve in math that works that way, where its y-coordinate and its slope are equivalent to each other. Another thing you can do with this type curve, y equals e to the x, again, with the base e, is continuous compounding. So, which I mentioned back on Friday. So we'll get to that soon. Right, so let's do example one. Example one. Right. So the first few examples, they're just doing some basic algebra rules. Remind you guys, exponent rules. E to the 7 times e to the negative 2. Okay. So if you want to see this out in expanded form, say, oh, what is that? How does that work? Remember, this is 7 e's multiplied. 1, 2, 3, 4, 5, 6, 7. Those are all multiplied. And then e to the negative 2. Well, it's divided by e to the 2. So you just do e. Right. Those two e's cancel out with those two e's. And you have these 5 e's left over. So isn't this just e to the 5? Okay. Now, a lot of you guys probably saw that from the outside anyway, because if you have a common base here and these values are multiplied, you can very simply add the exponents to get the new exponent. So 7 plus negative 2 is 5. Boom, same thing. Okay, so you know that. So that was example A. So 1A. Let's do 1B is what if you have negative 3 e to the 2x, and this is all raised to the 4. Okay? Well, this power 4 applies to all the parts inside it. Everything's multiplied. So this is really negative 3 raised to the 4, and then times e to the 2x, also raised to the 4. You get to think of it that way. Okay? Now, this negative 3 raised to an even power, that's just going to make a positive value, isn't it? Because negative makes a positive. If there's 4 negatives, still positive. 3 times 3 is 9, 3 is 27, 3 is 81. This is positive 81. Okay? And then this bit here, well, power to a power, can't I just multiply those powers? So I think that would be e to the 8x, like that. So that should be that answer. Boom. Okay. And then example C, 1C, we got 42 e to the 7 over 14 e to the 5. Okay. Well, 14 goes into 42 three times, so that would be 3. And then e to the 7 over e to 5, I can subtract the powers. That's e to the 2. 7 minus 5 is 2. Okay, boom, boom, boom. Okay. Okay, so nothing crazy so far. All right, and what's new is the base e, 2.71828, so on. Right, but the exponent rules here are what you've seen before. Right? Example 2, graph functions with base e. So let's consider, so example 2, right, let's consider a parent function. I'll say f of x equals e to the x. Right? And then they want to know, what does this new function they call it g of x look like? Where g of x is negative 2 e to the x minus 3, and then the whole thing plus 2. Right? Okay, so we're talking about translation rules. Translation rules. So I think that this minus 3 part right here would say go to the right 3. And I think this negative right here means upside down. This 2 means vertical stretch, factor of 2. And this 2 at the end means go up 2. Okay? And so starting from the parent function, put through that set of translations, and I should get the graph g of x. Okay. Let's put both graphs on top of each other here. All right, so let's call this x, y. Let's go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay, I think it should fit somewhere here. All right, so e to the x. Well, e to the 0 is 1, so 0, 1. All right, I'm graphing f of x first. Okay. E to the 1 is e, which is about 2.7 something. It's pretty close to there. Okay. And e to the negative 10, well, that's a tiny bit bigger than 0. So there's a horizontal asymptote going to the left at y equals 0. Okay. Put it all together, and here's what the graph y equals to e to the x look like. So I'll call this f of x. Okay. Now, if I take that f of x and put through this set of translations, I should get g of x. Right, so right 3. So if I take this point, go 1, 2, 3 to the right, and this one also comes 1, 2, 3 to the right. Okay, so I just drag the whole thing right 3. Okay. Let's put it upside down, so that will make everything negative. So this point flips down here. This point flips down here to about negative 2.7 right there. Okay. Then vertical stretch 2. So this is going to expand. The whole thing is about to get stretched by 2. So what was it? Negative 1 for the y coordinate. That's negative 2. And 2.7, well, negative 2.7 times 2, that's a little bit more than negative 5. So that's now way down here. Okay. So I'm watching it. So far, I've got a curve in my mind that looks about like this. But there's one last step. It says up 2. That's also going to take this horizontal asymptote and shift that up 2. So up here to the y coordinate, y equals 2. Here's your horizontal asymptote for g of x. Gonna go right there. Actually, maybe I should pinky it for got a different graph going on, right? Right. So here's the horizontal asymptote. Right. And then at this point at 3 comma negative 2 comes up 2, bam, right there. Oh, which is right on the x-axis. That's interesting. You could call it the 0 or the x-intercept. This point at negative 5 point something comes to up to negative 3 point something. Okay. So put it all together. I'm pretty sure g of x is going to look like this. I call it g of x. Okay. Now, of course, I can pull up Desmos and see, does f of x look like that and g of x look like that? Let's see, I think I got this ready to go. F of x, g of x, yeah, there they are. Right, those are those graphs. And okay, yeah, there's f of x in red and g of x in blue. And is this gray dot right here? Is this 3, 0? Oh yeah, it's 3, 0. Yeah, just like that. There you go. All right. Uh, Example 3, functions with base e. La Chandra deposited $1,500 in a savings account that paid 2.5% annual interest, compounded continuously. Ah, now we get to use continuous compounding. After 4 years, what's the value in her account? So, example 3. So, I remember there's annual compounding, uh, and then, well, here, I'll say monthly compounding. Just do a review right here. And then there's going to be continuous. compounding. Okay? So annual compounding, you could have the amount as a function of time is equal to the principal times 1 plus the interest rate as a decimal, all raised to the power of number of years that it passed. Okay? Uh, Now, if you want to make this monthly, then you're applying this interest rate. You're splitting up into say like 12 months. Right? So the amount as a function of time equals the principal times 1 plus, or I'll make it even more general. Let's do R over N to the NT, right? But then for monthly compounding, N would equal 12 specifically. There's 12 months a year. Okay? But what about continuous? Because the more continually you compound it, you get a tiny bit more money, tiny bit more. Okay? Now, this equation looks completely different than these two. I mean, these two are kind of similar. Because, okay, if I understand that, I can kind of get to that. Okay? This one is the principal times E, got our character E, to the interest rate times however much time in years, okay? Which is what we're using here. So for this particular example, they're calling the principal $1,500. So that's $1,500. And then times E, which is 2.718 something to the R. Now, remember, if the interest rate is 2.5%, as a decimal, that's 0.025, which is the number that goes in the calculator. Okay? And we're looking for 4 years, so the amount after 4 years equals, and then T would be 4, like that. Okay, so puts the calculator, so we get that's $1,500, second E to the power of 0.025 times 4. Okay? And that comes out to $1,657.76. It rounds to, like that. Okay. That's continuous compounding. Wonder what if it had been annual. Okay. So let's say A of 4 uh, annual. I'll say annual down here. Okay. We'll just run that real fast. Annual should be a little less than this. So take the principal 1,500 and then 1 plus 0.025, all raised to the 4. Okay. It would have been 1655.72 it rounds to. Yeah, so you get a couple dollars more out of this scenario by continuously compounding rather than just waiting for the entire year before you apply any compounding. Okay? Which actually brings me to a little side question that I want to do with you guys, which is what is the annualized equivalent uh, of a continuously compounded interest rate? Okay. Okay. So what I mean is, let's say, for example, here, we'll stick to the same interest rate they have here, 2.5%. Let's say the interest rate equals 2.5%. Right? So they're advertising, oh, yeah, so put your money in the account and we'll give you 2.5% interest, and that's how it'll grow nominally. But then you say, wait, is that 2.5% annually or 2.5% compounded continuously? Because those would be slightly different values. I say, oh, actually, it turns out it's continuous. Like, oh, okay. Right, uh, so continuously compounded. So what is this equivalent to? Like they could have advertised, the bank could have advertised a slightly bigger rate and just said, oh yeah, it's a slightly bigger rate, annualized equivalent, right? And what would that be? Right. Well, we can do this. Let's do A equals P e to the RT. Okay. Now I'm going to let principal be $1. You could make it any amount of money, but I think this is going to give you most obviously what the answer is. Okay? Times e to the, we'll go 0.025. That's what 2.5% is. Okay. And we'll let that run for 1 year. Okay. Okay. And then from this, you'll be able to see the answer is going to stand out. So let's take $1 and do e to the power of 0.025 and then times 1 year. So just go like that. Okay. And it comes out to $1 and 0. Okay, now I'm just going to put a string of decimals. I'm not going to cut it off at the cent mark. So 1.025315, okay, and it's just a decimal that keeps going on and on and on. Right, but let's just say it hit it out there. It's just to round it at some point. Okay. Well, if you subtract out the original dollar and say how much money has my account grown by, it's this bit right here, the 0.02, blah, blah, blah. If you turn that back into a percentage, that'd be our annual the annual equivalent would be this right here. So roll this over two, that's 2.5315% approximately. Okay. So that's the answer. Okay. So 2.5% compounded continuously is the same thing as 2.5315% compounded annually. Okay, so same thing. So if the bank advertised this or if they advertised this, it's equivalent scenario. Okay, example four, solve an equation using technology. Say using a graphing calculator to solve 5 equals 2e to the x. Okay. So I know what they want you to do here. They want to say, well, let's call f of x equal to 5 and g of x equal to 2e to the x, and just see where the curves cross and kind of sketch it out here. I mean, it's good practice to think like this. Okay. Then I'll throw this on Desmos and we'll see exactly what it looks like. Okay. Okay, so f of x equals 5. 1, 2, 3, 4, 5. Up here at 5. This should just be a flat line up at 5, wouldn't it? Okay, there's your f of x. Okay. And g of x, 2e to the x. Well, e to the 0 is 1, but then it's all times 2, so that would bring it up here to 2. Okay. E to the 1 is e, it's about 2.7 times 2 is a little more than 5, so that'd be kind of probably about here-ish above that peak line. Okay. And it would have the same horizontal asymptote as just e to the x. Okay. So put it all together. I'm pretty sure g of x is going to look like this. And exponentials, they take off real fast. So yeah, real sharp turn right there. G of x. Okay. It looks like they cross before you get to 1. So I bet it's like 0.9 something, maybe something like that. Okay. Um, so here, let's go ahead. Let's throw those into Desmos. Let's slide this up where I can get Desmos on the same screen here. Wank. Okay, so here, this one's from before. Let's do, call this 5. Let's call this one e, no, whoops, 2e to the x. That's what it is. 2e to the x, right? Okay, so there's my sketch of what that should look like. Yeah, it looks like Desmos got the same result. And this gray dot should be a little bit before x is equal to 1. 0.916 something. Yeah. Or, y value, of course, is 5. Yeah. Yeah. So that's it. So x is approximately 0.916. Yeah. 916. Uh, Now, you might say, well, here, if I'm trying to solve for x in an exponent, is there a proper algebra process where I don't necessarily have to graph it to figure out where they cross? Here, yeah, I should label this. So this is 0.916 comma 5. Right? Is there an algebra method? Yes, there is. And it shows up in module 8 in your book, I think. And I'll show it to you right here, just so you can have seen it once before we get there. Okay? So it involves logarithms. Right? That's kind of the proper way to solve for x from an exponent. Okay. So there are two logarithm keys on your calculator. One says log. Now that's logarithm with a base of 10. But right beneath it, there's a different key. It says ln. That's also logarithm, but it has a base of e, which also happens to be this base. So that's going to be perfectly applicable to this one. What I can do is take the natural log of both sides of this equation. Natural log of the left side equals natural log of the right side. Do like that. Okay. Okay, so what's that good for? Right. Well, when you apply logarithms, logarithms have certain rules associated with them. So I'll go through this process. If it doesn't click right now, that's okay. But in the future, when I properly teach this to you guys, then maybe it'll make a little more sense because you'll have seen it once. Okay. And so one rule with logarithms is that if you multiply two things within a logarithm, you're allowed to separate thus as two separate logarithms, right, and add these together. Right? So it'd be like that and that. Okay, okay, so let's see, I could subtract over this ln2, so ln5 minus ln2. Right? And then have ln e dx. Right? Another rule with logarithms, this is e dx. Right? Let's say if you have a log of a base to a power, you're allowed to take that power out in front. So this actually becomes x times natural log of e. Okay? And natural log of e, it turns out, and I'll show you guys, natural log of e to the 1, because natural log of e, okay, is 1. Okay? So this part is equal to 1, which means this whole right side is equal to x, which means this is the answer. So x is equal to natural log of 5 minus natural log of 2, which, by the way, was the same thing as natural log of 5 over 2. Okay, and I should get this number. Remember, x is 0.916. Let's see if I do. Okay, I'll try it both ways. What's natural log of 5 minus natural log of 2? 0.916. Sure is. Right, or I should say approximately equals. Okay, 0.916. Okay, or if I did it this way, natural log of 5 on 2. Yes, it's the same thing. Same thing. Boom, boom. Okay. And so there's three ways to do it. You graph that in Desmos or with your graphing calculator. Okay? And then when we get to module 8, we'll more properly go over this other method. All right, let's set the textbook puzzles. All right, number one, simplify. So e to the 8 times e to the 3. Oh, well, same base, different part, all multiplied. I can add the powers, e to the 11. Boom, done. Number 4, what's 2e to the 3x, all raised to the power of 2. Now, this power of 2 applies to both the 2 and the e to the 3x. So here, I'll write it out that way. 2 squared times e to the 3x being squared. Okay. Now, this power to this power, I can multiply those. So that's, all right, 2 squared is 4. And e to the 3x all raised to 2 is e to the 6x. It should be like that. Boom. Okay. You could, if you want to, plug in a value for x, like, oh, what if x is equal to 1 or pi or whatever crazy number? Okay. And this original expression will equal this boxed in expression at the end for as long as x is the same, of course. Number 7, I got 26 e to the 4, all divided by 13 e. Well, e is less like e to the 1, isn't it? Okay. Now 26 over 13, well, that's 2. This bit right here is just 2. 13 times 2 is 26. Okay. E to the 4 over e, that's like e, all divided by e. Because at least with 3 e's, it's e to the 3. Like that. Boom, done. Downstairs. Number 10. Graph the function, determine key features. Key features, I'm thinking, usually intercepts and asymptotes, but let's see what this looks like. All right, f of x equals 3e to the x minus 1, and then all plus 2. Oh, okay, we're doing translation rules here. Okay, so from the parent function, if the parent function was playing e to the x, right, relative to that, this is telling you go right 1, got vertical stretch factor of 3, and this last one says go up 3. Okay, so let's put that all together here. Got x, y. Let's go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's see what that gets us. So the parent function, y equals e to the x. Okay, so e to the 0 is 1, e to the 1 is e, 2.7 something. Okay, and there's a horizontal asymptote out this way, going forever to the left. Okay, string that all together. Ooh, yeah, inspect. Okay, string that all together. I think it'll look like this. Okay, so this is your parent function, which is e to the x. Okay, now what about f of x? So I'm saying these three translations right here. So let's take the whole thing to the right one. So this 0.01 comes out to 1, 1, and 1e comes out to 2e. Boing, boing. Okay, so I shift the whole thing. Imagine the whole thing shifting to the right one. Vertical stretch 3. So this will go up by a factor of 3 up here. Ooh, what is 3e? 3e. That's like 8.15. Yeah, I think I can fit that. 5, 6, 7, 8, 9, just a little bit above this. That's like way 5, 6, 7, 8, 9. It's like, okay, it's probably like way up here. Okay, so here. Okay, so now it's got super stretched vertically. Okay. And then finally shift the whole thing up 3. Well, that means this horizontal asymptote here is going to come up 1, 2, 3. Here's your new horizontal asymptote. Okay. This point at 1, 3 comes up to 1, 6 because we're going up 3. And this point goes way up and it's just going to go way up there. Okay, I wonder where this would crop the y-axis. And that's wherever x is equal to 0. I'm just going to plug that in the calculator because it's going to be some funny looking decimal, but it's going to be somewhere kind of in here, isn't it? Okay. So it's 3 e to the power of 0 minus 1. So I'm plugging 0 for x. And then the whole thing plus 3. I'm going to make a guess. It's probably somewhere around 4-ish. Oh, yeah, 4.1 something something. Okay, and it's a funny decimal, 4.10 something something. Okay. So that's right about here. Okay, so yeah, string that together. Gonna go like this. Right, and there you go. There's your f of x. Boom. Dunskies. Of course, you could confirm that on Desmos. That's just what it would look like there. At 15, investments. Marcella invested $12,750 in the company. Her investment has been growing continuously at an annualized rate of 5.5%. Write the function that represents the situation, and what will our investment be worth after 9 years? Okay, so let's do that. So they're telling you the principal is 12,750. The interest rate is 5.5%. As a decimal, that's 0.055. It's per cent. It's literally per hundred. Well, the decimal over two places, right? But that is okay. It says continuously though, which tells us how we're going to craft this equation. So the amount after some time is equal to the principal, $12,750, times e to the RT. Here's your R, and then T is however many years. Okay? So that's what they're looking for. Right? And then how much after 9 years? Well, that'd be A of 9. So let's do 12,750 times e to the 0.055 times 9. Right, just put a 9 where the t goes. See, what is that? 12,750. Second e to the power of 0.055 by 9. I'm looking at $20,000, 916, right, and then 35 cents. Yeah. Right. Uh, Earlier in this lesson, I had a side question that said, hey, if it's 5.5%, but continuously compounded, then what's the annualized equivalent? Right. So I'm going to come up with my own question C. Okay. What is annualized equivalent interest rate? Okay. So let's do A equals PERT. Okay. I'm gonna here, I'll just do this on my calculator screen. So I did this earlier, but it's calculator screen. Okay. All right, so principal, I'm going to call it like $1. Okay. Then second, e to the power of. This interest rate is 0.055%. That's first continuous compounding. Let that go for a year. Okay, it turns out like this number. So subtract off the original dollar, say how much should we accumulate, and times 100 to turn that back into a percentage. But so here, skip, skip, skip. I did this all on my calculator screen, and I verbally walked you guys through it. It turns out that the rate annualized would be equivalent to 5.6541%. Okay? So if the bank says 5.5% continuous compound or 5.65% annualized, okay, right? So it's like the same value. All right, what's next here? 19. Oh, using a graphing calculator to solve, so might have to be pulling out Desmos here. System equations round to the nearest hundred. Yeah. Okay, 19. We got 5 equals 1/2 e to the power of x plus 2. And the whole thing minus 4. Okay. Yeah, so this will create a graph that looks kind of like this. And then 5, of course, just a flat line. There's just some point where those two are going to intersect. Okay? So I could say f of x equals 5 and just get a flat line. They could say g of x equals 1/2 e to the x plus 2, all minus 4, get different. Okay. So let's go into Desmos here. Here, slide this up where I can see that as I type those into Desmos. Desmos time. Oh, I got f of x is 5 already. It's already ready to go. All right, and then right here is going to be 1/2. Oops. Oh, nope, that was okay. 1 over 2. Okay, e to the power of says x plus 2, and the whole thing is minus 4. Okay, I think that's right? Is that okay? All right, and this here, let's expand this bigger. You guys see what the graphs look like? Wherever that gray dot is has to be the answer. 0.89. So that's the answer. Okay, here, I'm gonna write that down on paper. Okay, so x equals approximately 0.89037. Okay, 89037. Okay, somewhere there. Okay. So back over here. Okay. There's your x value. Of course, the y value had to be 5 because it's 5, right? Okay. Yeah, so if you plug that in for x right here, bet you get about 5. Oh, oh, this is a decimal approximation. So it might not be exactly 5, I bet 4.99. So, okay, we're going to find it. Let's do zero point 0.5 for half. Okay. Second e to the power of x plus 2. That's like 0.089037 plus 2. Okay, and then close parenthesis, and the whole thing minus 4. Let's see if I get something very, very close to 5. But it 1 half e to the, oh, whoops, got an extra 0 in there. Get rid of that. Right, there you go. There you go. Right, exactly. So 4.9999. Oh, okay, that's basically 5. We're good. We're good. All right, number 29. Uh, okay. Oh, solve this equation. Ooh, a little fancier. Got negative 3 e to the x, and the whole thing plus 1. And that's equal to 4 e to the x plus 2, and the whole thing minus 5. Okay. Now, okay. There is a way to solve this properly with logarithms, or it could make y equals this, y equals this, and solve it with Desmos. Okay. Let me show you guys the proper way with logarithms. So I could do, let's do plus 5 plus 5. Let's do that. So I'll get 6 over on the side. I'll do plus 3 e to the x plus 3 e to the x. Okay. Is equal to 4 e to the x. Mm, power rules. This could also be e to the x plus 2, same thing as e to the x, e to the 2. It's the same thing. Right? Right. But I need to add over this 3 e to the x. Right? Now I do see this e to the x there and there, so I can factor out all the that coefficient. So that's 4e squared plus 3, then e to the x. Okay. So e to the x, I could take this, divide it down, 4e squared plus 3. Okay. And then take the natural log of both sides. Well, that would just give me the answer. So x equals natural log of all this. Okay. So again, this is module 8, but let me see what number I get, and then I'll throw this into Desmos and see if it matches. So natural log 6 over 4e squared plus 3. 4 squared plus 3. Okay. I'm looking at x as approximately negative 1.6912, something, something, something. Okay. All right. How about if I plug each of these functions into Desmos? Desmos time. All right. So I'll call the left side f of x and the right side g of x. Okay. So negative 3e to the x and the whole thing plus 1. Okay. And this one down here is 4e to the x plus 2. Nope. X plus 2. There we go. No, that's not. Why does it not put that up there for me? Okay. Let's do open parenthesis. There we go. That looks better. Okay. And the whole thing minus 5. Okay. Okay. Where's that gray dot? Is that gray dot? Does it have an x value of negative 1.69? Yeah, sure does. Negative 1.69. Blah, 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 blah. Right. There's also a y value for that matter. 0.44 something. If you wanted that. All right, there you go. Solved. Solved. Oh, yeah. All right, and here, I'll do one more with you guys here. Close this out. Find the zero in this function, round to the nearest hundredth if necessary. Ooh, here, just gonna set this up right here because I'm just gonna use Desmos to find this. We got f of x equals 0.8. Let's work this if you like. E to the 2x, and then the whole thing is minus 9. All right, so there's your function. Okay. Now I'll type that into Desmos. Okay. And when it says find the zero, that's the same thing as finding the x-intercept. So let's bump this one. F of x equals 0.8 times e to the power of 2x. Okay, and then the whole thing minus 9. Okay, so wherever this curve crosses the x-axis is the zero. There it is, about 1.21. So x is approximately 1.21. Okay. And there you go. That closes out 7-3.